Welcome back, everyone. We are on to the last video of our Laplace series, and specifically now we are looking at the Laplace of a differential equation. So this is a really good explanation of why we cover Laplace. Remember, Laplace is a translation of variables, specifically so that I can deal with a differential equation or an integral equation in terms of polynomials. And so this gives us a really good idea of why we want to go ahead and do it, because we understand things. I will point out I'm just covering the basic stuff with how to deal with the Laplace of a differential equation in this video. And in another video that we have, which is about the operational properties of Laplace, you can get Laplaces of differential equations that have all of those operational properties included. So just keep that in mind. Check out both and make sure you get tons of practice in when you're doing those. Okay, so let's talk about the general steps when you're doing the Laplace of a differential equation. So when you're doing it, of course, you want to start with a differential equation. And by that, I mean we're looking at something of y prime plus some by prime plus c, which is equal to something on the other side. Let's say it's just another constant d. Instead of a constant, you can instead have other equations, or you could have something that looks like those translational properties, and the list goes on and on. But generally, this is what a differential equation looks like. We've talked about other ways to go ahead solving it, and the Laplace is just another way that we can try and solve for our initial y function. So then when you're talking about taking the Laplace of the differential, this is where we start. Then we're going to take the Laplace. When we end up taking the Laplace, we keep in mind, there might be a y here, there might not. When we go ahead and take the Laplace of this differential equation, what we want to keep in mind is that these guys have special equivalences associated with them. So the Laplace of y prime is going to be equivalent to s squared y of s minus s y of 0 minus y prime of 0. Then the Laplace of y prime is going to be s y of s minus y of 0. And then that third one, the Laplace of y, is just going to be equal to y of s. So you're going to take the Laplace of everything. Any functions you would do the normal Laplace of. When you have these y and y derivatives, you're going to plug these things in. And then we're going to go ahead and solve for y of s. We want one y of s function, because that means if I have y of s is equal to something crazy and I do the inverse Laplace of both sides of this function, this goes back to being y of t, which should be my original function, and then I have all this crazy stuff on the other side. So then I don't have to deal with the kind of undetermined coefficient stuff that I've had to deal with before. So yep, step 3 is going to be solve for y of s, and then step 4 that we're looking at is taking the inverse Laplace. When you're specifically asked to do the Laplace on a differential equation, these are the steps you're always going to take. If things are a little bit weird, like one of the things we consider early on with trying to find a function is the integrating factor stuff. That means that this is not a function. This is not just a constant. That makes things a little bit harder to go ahead and do the Laplace of it, because then you're looking at a Laplace of two functions being multiplied to each other, and that's hard for us to go ahead and deal with. So typically anything on that is a coefficient on y prime, y double prime, or y is going to end up being a constant value, and then all other non-constant values are going to be the right hand side. That just makes things a little bit nicer. Okay, cool. Then we're just going to go ahead and look at some examples. So my first one I have is y double prime plus 5y prime plus 4y is equal to 0. Generally, the other thing that we consider with Laplace functions is initial values. And then y prime of 0 is equal to 0. This is a 5, I swear. This is a good example because all the stuff on the left-hand side of my function has a constant coefficient, just like it should. Also, I have a 0 on the right-hand side, not a big deal. Technically, like I mentioned, this could be anything. This could be a delta. This could be some f of t minus a function with a translation. This could be two things multiplied. Anything and everything could be over there. Okay, but now that I have my differential, my next step is to go ahead and take the Laplace of it. So when I do that, I'm just going to go straight to the next step. You can go ahead and keep in mind the linearity properties of Laplace and break it up. That's fine. I will just go ahead and skip, and I recommend you looking at how that works. So when I do that, I end up with s squared y of s minus s y of 0 minus y prime of 0 plus 5 all multiplied to sy of s minus y of 0 plus 4y of s. And then we're going to plug in these. This is a 1, I swear. Okay. And currently this is still equal to 0 because the Laplace of 0 is still 0. Can't do a change of nothing. So then I'm now looking at the function s squared y of s minus y of 0 equals 1. So I have an s here. This goes away because it's 0. That goes away because it's, that actually does not go away because it is positive. Then I have plus 5sy of s minus 5, right, because this ends up being 1 multiplied to a 5. And then this is just 4y of s. So I'm going to move everything that is okay onto the other side. So then I have s squared y of s. By okay, I mean anything that doesn't have a y of s attached to it, plus 5 s y of s plus 4 y of s. So on the other side, I just have s plus 5. Then I'm going to factor out my y of s term, and then I have s squared plus 5s plus 4 equal to s plus 5. And then y of s is equal to s plus 5 over s squared plus 5s plus 4. We're going to go ahead and factor the denominator and see if anything works out nicely for us. So then I have s plus 5 over s squared, except if I factor, it's no longer squared, plus 4 plus s plus 1. Not great for us, but that's okay. This is a good chance for us to see why partial fraction decomposition is so important for us when we're talking about differential equations. Because I get here, and this does not look like anything in my charts. Remember, whenever I'm talking about Laplace, when I'm doing forwards or backwards, I want things to match my charts as perfect as possible, and that does not match any of my charts. So I need to go ahead and do partial fraction decomposition. I'm going to do it really quickly. Do keep in mind that we have a video on it. So if you don't feel comfortable doing partial fraction decomposition, please go ahead and check that out and try out all of the techniques in there. So if I'm considering this as being a of s plus 4 plus b over s plus 1, then I end up with a times s plus 1 plus b times s plus 4. This is s. So then when I end up doing that, that one ends up going away, and then I end up with 4 is equal to b times 3. So then b is 4/3 And then when I do that and plug in -4, I get 1, which is equal to, and then A is equal to -1/3. Okay, and then I can go ahead and plug that in. I will probably change that a little bit and consider it as -1/3 out in front and then 4/3 out in front, because that makes it a little bit easier when I go ahead and do the Laplace anyway, although you could put it in the numerator too. Then now that I've completed everything and I've gotten my right side looking good, so I can go ahead and take the inverse Laplace. I take the inverse Laplace, which is just the inverse Laplace of y of s and the inverse Laplace of my simplified, nice looking right-hand side. That means I end up back with my y of t, and specifically on the other side, I have -1/3 e to the -4. Actually, I think it's +4. Negative. Plus 4/3 e to the -t. Let me double check. I believe it's positive. Yeah. So those become negative because this would normally be s minus a. Okay. And so that is our solution for y of t. Coolio. This you could also do by like some of the processes associated with undetermined coefficients. It's just, you know, there are going to be tons of ones where it's way easier to do this. Also, if you feel way more comfortable with plus, this is easier to do. Okay. I have one more example where I can't solve for some of my values, and I have stuff going on the other side. Okay. So I'm going to clear all my drawings. So I have y double prime minus 4y prime is equal to 6e to the 3t minus 3e to the -t. And both my y of 0 and my y prime of 0 are equal to 0. Okay. Now let's look what's going on here. Again, this is gonna, we have our differential equation. So our next step is to go ahead and take the Laplace of it. Again, I have s squared y of s minus s y of 0 minus y prime of 0. That is ugly, but that's okay. And then I have 4 s y of s minus y of 0, which is equal to, and then on the right-hand side, I'm doing just the Laplace of those, which is going to end up being 6 over s minus 3 minus 3 over s plus 1, with a plus sign in between because I moved the negative up in the numerator. Personal preference, don't worry about it. Then I need to go ahead and move things around. This is going to go away, this is going to go away, and this is going to go away since both y of 0 and y prime of 0 are equal to 0. Then I have s squared y of s minus 4s y of s, which is equal to 6 over s minus 3 plus -3 over s plus 1. Then I need to essentially pull things out. And then I have s squared minus 4s, which is equal to s over s minus 3 plus -3 over s plus 1. Okay. I'm going to take this thing and put it in the denominator of both of these, simplified, right? Because this is technically s and s minus 4. So that means on the right-hand side, I have 6 over s minus 3, s minus 4, plus -3, s plus 1, s minus 3, s minus 4, which means I have two fractions that I need to go ahead and do partial fraction decomposition with. Again, I'll go through that process really quickly, but if you want more examples, I accidentally erased my 6. We do have a video. Okay. So when I do that, I get, so let's say that this is a over s plus b over s minus 3 plus c over s minus 4. So 6 is equal to A minus 3, S minus 4 plus B, S minus 4 plus C, S minus 3. Okay, so if I first plug in 0, those two go away, and then I end up with 6, which is equal to A times -3 times -4, which is positive 12 over 6 over 2. 6 over 12 is 1/2. So A should be equal to 1/2. Then I will plug in, I'm going to move that over. I guess I'll just go ahead and erase, and we'll talk about the next one. So A should be equal to 1/2. And so then if I do S is equal to 3, that means that one goes away and that one goes away. And then B is equal to 3 times 3 minus 1, which is a -1. So this is -3. Divide it over. B is now equal to -2. So then I can go ahead and plug in 4, which now I have a little bit more room. And this one's going to go away, and this one's going to go away. And then I get C times 4 times +1, which is just 4. So I simplify that, move that over. So C is equal to 3/2. And then I can do that. (1/2), -2, 3/2, and now I need to consider the other one, which since I've already found my A, B, and C, I'm just going to go ahead and do this. A of S plus 1 plus B of S minus 3 plus C of S minus 4. Which means I end up with -3 is equal to A, S minus 3, S minus 4. Plus, did I move something? Oh, this should be S, not S minus 3. And this is why we go a little bit slower. So this can always happen. I did S minus 3 instead of S. Remember, this was ending up being S squared plus 4 times Y of S, which simplifies to S and S plus 4. So S and S plus 4 should have gone to each of these. Instead of doing that, I replaced this with S minus 3. It happens. Keep in mind that things may not always make sense. Watch out for it. Once you get to the end, one of the things you can go ahead and double check with when you're talking about Laplace is, you know, Laplace of, like, you can go ahead and take your y of t function in and plug it into your original and see if it makes sense. That might be a little bit hard, but it is doable. So then I have B, so this should be S instead. And then I have B being multiplied to S plus 1 and S minus 4, and then C being multiplied to S and S plus 1. So then I'm going to go ahead and plug in 0 again. So I get -3, this is going to go away, and this is going to go away. And then when I plug in 0, I end up with 1 and -4. So then I would divide it over, so B is equal to 3/4. Then I'm going to do S is equal to -1. So then I get -3, which this then becomes -1 and -5. This will go away and this will go away. So A is equal to -3/5, because negative and a negative is positive, divided over negative. And then at the last one I need to do is plug in 4. So -3 is equal to, that one goes away and this one goes away, and then C times 4 and 5. So I get -3 over 20. Good times. Okay, and those are going to replace it. you would then go ahead and just like normal, you would take the inverse Laplace. And this one is pretty complicated just because there's lots of terms, but besides that, things are actually kind of nice for us. And if you wanted to, there's a couple things that could combine and make that a little bit easier for you, but don't worry about it. So yeah, this is now your expanded y of s function, and you can go ahead and simplify from here by taking the inverse Laplace. Go ahead and try that for yourself. Besides that, I think that covers everything foundational about doing the Laplace of a differential. Like I mentioned, instead of a simple function on the right-hand side or a constant, you could end up with something like one of the translational properties and have to deal with that. But you would treat it just like here, where you're kind of dealing with the left hand independent of the right-hand side. And so then you're just solving for y of s, separating things out, and making things a little bit easier for yourself. Okay, good luck everyone. Have a great rest of your day.